All right, great. So welcome to this first official kickoff talk in the Montreal Robot Learning Series. We've had a few talks before this, but it wasn't called the Montreal Robot Learning Series. We're super excited to have Florian Shkurti here to give this inaugural talk. I've known Florian for several years. He used to be a PhD with Greg Dudek, and so we met in Montreal. And now he's an assistant prof at the University of Toronto, really taking the U of T Robotics Institute to new heights at University of Toronto. He directs the Robot Vision and Learning Lab, which I guess is a relatively new lab that he'll tell us about. And his research really spans, I think what's interesting is a lot of really interesting applied work, like some of the video that we're seeing right now, and then connecting that with novel learning-based methods related to Bayesian approaches and and imitation learning and such. So without further ado, I'll hand it over to Florian, who's going to tell us about algorithms and systems for robot videography for human specifications. Thanks again.
All right. Thanks very much. Thanks for the kind introduction. And congrats again on getting the seminar started. It's going to be an interesting seminar series. And I really like the focus on robot learning, especially. So my name is Florian. I'm an assistant professor at U of T, working on robotics, informed by machine learning and computer vision. And today I wanted to talk about algorithms for robot videographies and the general, the general idea behind many of these systems that you're going to see. The general question is where should robots look? So the plan for today is to give an introduction and an overview of my research agenda, then to talk about the problem of robot videography from human specifications. And then we're going to talk about where should robots look in terms of localization and SLAM and active sensing. And if time allows, I'm going to talk about a new direction in my lab, which we're very excited about, and for which we have a new paper under submission. And I'm going to talk about how it connects to the remaining agenda that you had seen so far. But the central technical question, as I said, is where should robots look, and why, of course. So just a bit of overview of the areas represented in my lab. So my lab does work on robotics, informed by ML, perception, control, and the guiding questions that we use in order to inform the problems that we work on. Are how can humans specify the behavior of the robots without writing code? So the idea is that we're going to have lots of robots appearing and being used in everyday scenarios, but not every person is going to be an expert. So how do you get your grandma to specify a task for a robot without necessarily knowing how the robot works? And how can robots safely and robustly learn to execute the desired behavior over time? With emphasis on safety and robustness, obviously. So the main application areas that I find interesting personally are environmental monitoring, autonomous vehicles, and human-robot interaction. And I'm going to talk about this research agenda in a bit more detail, but the general three threads that I see myself sort of including in my research agenda are autonomous robots for environmental monitoring, and especially the problems related to visual attention and where should robots look. Problems related to machine learning for planning and control, and safety in learning via better simulation. And I'm going to go into these into a bit more detail before I go into the main topic, which is the first thread. So I think we need to design better simulators for not just for the sake of approaching and closing the simulation to reality gap, but I think there is something to be said about simulation helping to certify robots. And in order to get there, we need to be able to generate adversarial scenarios in simulation that can transfer to the real world. We need to be able to say that the risk metrics that we're using in simulation can also transfer into the real world. And in order to do that, in order to avoid treating these simulators as black boxes, which we currently do, we need to essentially do work closely with the graphics community on ensuring the differentiability of the simulators. So differentiable rendering and differentiable physics. If we manage to do that, we're going to be able to have better chances of ensuring that robots that we train in simulation can safely do the task in the real world. And my lab also has ongoing work on safety during exploration in RL, which is a very interesting and complicated problem. So in terms of machine learning for planning and control, we're looking into imitation learning, shared autonomy, and continual learning, where the idea is that the dynamics and the behavior of other agents in the world is changing over time. But today I'm going to focus mostly on autonomous robots for environmental monitoring and the questions of visual attention and search. And I call this sort of direction robot videography from human specifications, and I hope you will see why in a bit. So the main problem here is that even though we've made a lot of progress in monitoring large natural environments in multiple ways with multiple robots, we still have issues regarding how to tell these robots what's useful and what's not. So we have physical oceanographers, we have biologists, geographers starting to use drones and underwater robots and things like that. We even have robots on Mars. But all these people who are scientists and are experts in their fields, they're not interested in the robots are just a means to an end for them. So they're not interested in actually in deploying the robot, but they're interested in the data that the robot is going to collect. So how do we help scientists get better data in the field? In other words, how can we help them specify the type of data that they want their robots to collect easily without a lot of manual annotations? So I think that's one of the main questions in this line of work. And in order to answer that question is sort of related to the more general question of where should robots focus their cameras? Where should they pay attention to in a large scene like this, where they're called upon to cover a large part of a large volume of the real world? They cannot possibly spend time, covering the entire area. Where should they focus? So if you ask a marine biologist what's important in this scene in particular, she could say that she's looking for footage of coral reefs. And you can sort of isolate the coral heads that are interesting in this scene. And this is nice, this is interesting, but we're more after her reward function and her decision-making process as a scientist, rather than just labels for this particular scene. So we'd like to get the reward function of the scientist. And it is worth mentioning that there are two aspects to this problem. One is the exploitation and search, which is collecting useful data. And the other one is the aspect of exploration, which is about collecting surprising observations and trying to minimize your epistemic uncertainty about the true model of the world. So exploration is about reducing the valid hypothesis space, and search is about getting more useful data that the scientist is interested in. And when it comes to exploration, there is a lot of work in the robotic setting from Yogesh Girdhar and Greg Dudek. There's also a lot of work in terms of reinforcement learning in the field of intrinsic motivation. So we're not, and there's also the added complexity of, if you only pursue surprising observations, that doesn't necessarily mean that you're going to get useful data for the scientist. So chasing after surprise doesn't necessarily lead to useful data. So that's why we decided to ignore the exploration problem for a bit and focus more on search and the exploitation aspect of the problem. And the first version of search, at least how we thought about it, the simplest version is Katrin saying, okay, I'm looking for footage of coral reefs. Try these waypoints that I'm going to give you. So in this case, so this is how most of these vehicles operate at the moment. The second is Katrin saying, okay, I'm going to annotate as many images as I can, and I'm going to let you build a model of what's interesting and what's not. So that's also a valid approach for this type of thing. The approach we're interested in, and which I'm going to explain in a bit, is here's a single example of something that I find interesting. Try to collect more data like this. And the reason this is interesting and useful is that it sort of makes the annotation process, the supervision process, if you will, it makes it much easier for the scientist because now she doesn't have to annotate a ton of data. And it's a bit more interpretable in the sense that she can interact with the system in a way that makes more intuitive sense. So this specifies the reward function over images. And then version 4 of the system that we recently showed a few months ago before everything shut down was, okay, I have some waypoints that I'm going to give you, but they're going to be advice. So search for interesting images like this one, but try to keep close to these waypoints that I'm going to specify. So this is a compromise between the last two approaches. And I'm going to talk about this in more detail as well. So exploration and search version 1.0 was done, we did it quite a few years ago, and it involves a multi-robot setting where a plane, a boat, and an underwater robot collaborate in order to get useful footage for Katrin at different scales of the map. So the idea is that the aerial vehicle is going to give you very high-level footage of what's available on the beach. That footage is going to go through the internet to Katrin. She's going to annotate what are the interesting waypoints. Those waypoints are going to go back to the boat and to the underwater robot, which is going to do essentially waypoint following using vision and a bit of visual navigation in order to go closer to the reefs and collect a bit more useful data. But this is essentially the crux of this is waypoint following. And the robot is going to go up on the surface for a bit in order to get GPS readings because, as many of you know, there is no GPS underwater. You can have alternative systems, but they're expensive. And then the footage goes back to from the underwater robot to the boat through the internet to Katrin, and she can make the scientific remarks that and notes that she needs on the footage that she got back. And this got quite a bit of traction in the press, which was nice. But and as a retrospective, sort of, we really liked this type of system. Working with scientists was very rewarding, and this was the first experiment of its kind, or one of the first. But the major disadvantages, as you can see, is that the scientist has to be in the loop while the robots are running. So there's not a lot of autonomy, and there's not a lot of shared autonomy in a sense, and the scientist is way too involved. But most importantly, robots have no idea what the scientist wants. So all the remaining experiments and systems are essentially a way to try to fix these two issues. And just to drive this point home, most of these robots, including most of these robots that are shown here, actually do waypoint following in some coordinate system. But the onus of where the robots should look, it falls on the user. And actually, it falls on the user before deployment. So there's not a ton of room for adaptive sensing and reacting to the things that the robot observes in the environment. This is slowly changing, by the way. And we, even 2-3 years ago, you could see more active sensing on Mars rovers as well, where they allow the camera to focus on more useful information without the scientists being involved. So the second approach about trying to improve on that first experiment is to annotate as many images as we can and build a model at the semantic level. So you can start doing semantic segmentation type of training where you annotate, where you say what parts of the scene are interesting, and you can get a pixel level reward in a sense. So this is related to issues of visual attention, which have completely different treatments in the vision community and in the biological vision community, and in particular, we need to talk about some of the contributions of Tsotos and others in this field. But this is related to top-down visual attention, where there is a specification on the top, and that changes the behavior of the attention mechanism. And you essentially get some sort of a selective tuning, but without a lot of learning components. So the main idea here is to only request annotations for the most informative images. So how can we do that? So which active learning criterion should we use for semantic segmentation? And I have a few slides about active learning and what's aleatoric and epistemic uncertainty, but I think it might be safe for this group to assume that it's well known, unless someone raises their hand and tells me that they don't know this. Can I skip this? I think I'm going to safely skip it. So the idea here is that we want to do active learning in the space of weights for the neural networks. So we want to take into account the different distribution over a posterior over weights for the neural network, and we want to ask the scientists to label the images that are going to have the images whose annotation is going to give the highest information. So we want to compute the mutual information between the label that we expect to get and the weights of the network. And unfortunately, if you try to evaluate this using either of two available ways to evaluate it, you're going to figure out that you need to sample from the space of labels, which in this case are semantic segmentations. So you cannot just take an easy sum over a few classes like in full image classification. Here, the space of labels is, k to the n. So this is difficult, and we avoid computing this mutual information by essentially keeping an ensemble of rewards using either the bootstrap method or test time dropout, and we choose the image with maximum disagreement in terms of average prediction. And if you compare this sort of active learning, active selection of which images to annotate compared to a random selection of images to annotate, you're going to see that you only get modest results. So active learning is not going to help us here. It's not going to help the scientist to quickly get to the specification that that she needs to get. So that's why we moved on from that approach, and we focused more on the approach we're going to see here, which is one-shot visual search. So, so the idea is that the scientist is going to give us an exemplar image, and we're going to find representations that allow us to make easy comparisons between the image that the robot currently looks at and the exemplars that she gave. And you can see here, for example, that the first exemplar is a brain coral, which does not necessarily appear in the scene. So these are not objects that we assume are in the scene, but they are related in terms of class. And it modifies the behavior of the heat map so that it focuses on the brain coral and specifying the diver, which again doesn't appear in the scene. And it's from a completely different viewpoint from the diver that you can see in the image. That also modifies the heat map so that the attention mechanism focuses on the diver. And we want to do this without fully training, without doing supervised learning, essentially. So how do we do that? We assume that we have a lot of videos of underwater footage, and we extract key points and we track them over time in the same way that you would do it during in a SLAM front end, for example. And this gives us local similarity across time and and we also assume that tracking these key points is going to allow us to look at the same patch from slightly different viewpoints. And we are interested in long patch sequences with viewpoint variations, so that we can sort of impose invariances on the learned representations to be the same for each of these patch sequences. So this is a local version of similarity, and we'd like to get a more global version of similarity. So we resort to hierarchical clustering. So initially we cluster these patch sequences using a CNN encoder pre-trained on ImageNet, and that gives us an initial hierarchical clustering. But then we ask the human to intervene at the high level by either splitting groups or merging groups. So the user now doesn't have to annotate at the pixel level, but they just have to shuffle some clusters around, and that cuts down the interaction time dramatically, to the point where we can actually use these types of clustering methods in the field while doing experiments. So it cuts down the supervision time from days, which is what we had with semantic segmentation, to a matter of a couple of hours with this type of scheme. And then when we get we can refine the initial clustering using the additional data that the user gave us, and then we optimize the representation so that things that were deemed to be similar by the refined clustering are actually close in terms of learned distance from this representation, and things that are different are far apart. So this is done through a triplet loss, and the whole idea behind contrasted learning. So during deployment, we get an input image and an exemplar patch, and we compare essentially the representations and the embeddings from these two, and we create the heat map using a convolution. And when we essentially evaluate this type of technique compared to other methods like information invariant clustering or conditional VAE or pre-trained networks on ImageNet, we see that the representations that we learn are better because we make use of weak supervision. But they're much more useful than the other fully unsupervised representations. So how we make use of the system in the field, we have this robot which has two cameras, one looking forward, tracking the diver, and the other one looking downwards, and it's used as the main videography camera. So we want the videography camera to record interesting things while the front camera is not losing track of the diver. So you're going to see the robot rolling in this video because it's realizing that the data at the bottom is not as interesting as the data on the side. So it's evaluating its saliency, its visual attention heat map, and based on that, it's making decisions about where to direct the videography camera. So it periodically is going to check if there's anything interesting downwards or on the left. And if it doesn't detect anything interesting in terms of saliency, it's going to go back to looking at corals. So in this case, the exemplar image is brain coral. So the robot is going to focus on detecting corals. And eventually, when it goes to another side, you can see, and corals start appearing on the left, you're going to see the robot rolling in the opposite direction. Here. So the type of recorded images you get using these rewards are, the whole idea behind using the scheme is that if you take into account this reward-based strategy during data collection, you get more textured data, let's say more data of corals than if you randomly roll or if you periodically roll every 10 seconds. So you get a more informed camera, so to speak. And you can do the same scheme without relying on the diver. So here, the robot is realizing that the diver is going in a direction where there's not as many interesting things, so it decides to deviate and tries to navigate on its own. So the visual navigation window is essentially an obstacle avoidance strategy where the red and green bars show the probability distribution of pitching and yawing. So what's going on here is that the robot both avoids corals and tries to direct the camera to the front camera towards interesting things. And eventually it's going to find an interesting site. It's going to start circling around it as a way to notify the diver, to alert the diver that there's something interesting in there. The diver is going to go acknowledge that they received the message, and he's going to roll the robot a bit in order to tell the robot that it can move on to the next search mission. So there are a large number of human-robot interaction challenges, as you can imagine. Most of them are related with how you can notify, how one player can notify the other player of whether they saw something interesting. So how can the robot notify the diver and the other way around? And how can they coordinate to partition which areas to explore so that they don't, look at the same area over time? And this is all in the presence of severe communication constraints, both in terms of acoustic channels and optical channels. Yeah. And we do not, there's a lot of work to be done in this domain. We do not claim to have addressed it. So the fourth version of this search is essentially deviating a bit from a set of given waypoints and trying to still explore around, do constrained exploration around those waypoints. So the general idea here is that you want to learn to navigate, you want to do informed exploration and scientific data analysis in a circle where all these modules are improved over time. So the main idea here and the main way we execute this is we start with behavior cloning by training a behavior imitation policy to regulate the pitch and the yaw of the robot in order to avoid obstacles. So this is this is essentially a very reactive policy, but it's not goal directed. So we need to make it goal directed, which is where the hindsight relabeling comes in. We use a local state estimation module, and we augment the imitation, the behavior cloning data set with state estimation data. Then we pretend that that some of the states that were visited were actual goals of the robot, and we retrain the policy. But now we add a goal as an input. So we train a goal conditional imitation policy from data that was entirely non-goal directed, leveraging the fact that we have state estimation data from vision and an IMU. So this allows us to do things like this, where we can specify a coordinate and the robot is going to visually try to go there in that direction while avoiding obstacles and going on top of that coral, as you saw. So we have data to show this in the real world as well, but I thought it was much better illustrated in simulation here, where the robot wants to go in the straight line trajectory from A to B, which is the sort of orange or beige type of line. But it actually decides to deviate because it sees more interesting corals on the side while still hitting the goal. And in all these maps, the robot is trying to sort of deviate slightly from the specified waypoint sequence in order to maximize the interestingness of data that it's going to collect by traveling nearby. And again, all of this is done visually. So moving on to another question of where to look, this time during SLAM. We have in joint work with, also I should mention that this last work with goal conditional policies was led by Travis Manderson at Mobile Robotics Lab at McGill, Travis and Juan Camilo. And we have this, we used to work on stereo-based and inertial SLAM many years ago. And one of the questions that always came up was, how should the robot travel in order to help SLAM perform better? And this was particularly true in aerial deployments, where you have a large part of the scene that is very far away from the camera, and if you focus on that part of the scene, you're not going to get good triangulation. So achieving robustness in SLAM has a major component of actually deciding where the camera should look. So in these two cases, at least for triangulation-based systems, and I'm not speaking in general for all SLAM methods, because there are some that are more robust than others, and there are many ways to avoid these problems. I think the two main problems in visual SLAM, at least, are, or in SLAM that uses triangulation, are that the camera shouldn't look at places where there is not enough rich texture, and the camera should not look at places where there is texture, but they are too far to be, features are too far to be triangulated. So the vast majority of existing visual SLAM algorithms fail when these red areas grow too large, so because you don't have enough signal. So we need to have texture-seeking robots that essentially decide to look where it's most useful for the algorithm in order to help the algorithm do better. So what we did was we trained the regressor, which, given a patch, is going to try to predict the number of key points in it. And also, we can, given that patch, we wanted to, we could also predict whether the triangulation was going to be reliable, in the sense that the uncertainty around the triangulation, the uncertainty around the position of the point that's being triangulated, we wanted to have that be small rather than big. So when you do this, you get robots that sort of try to look mostly at buildings because they are most stable, and you essentially the robot has to move slow so that the robot it can evaluate the usefulness essentially of all these points. And at the same time, it has to train the regressor online and update the regressor online in order to keep a better prediction that is tailored to the scene. So when we evaluate it indoors, we get things like this, where we're with fixed gaze, the robot cannot reconstruct the entire trajectory. But when using the active gaze and the robot is allowed to look wherever it wants, you get a full completion of the trajectory. In this case, it was because the robot decided to put the camera looking upwards on the ceiling in order to get more stable features that were at the same distance, which was surprising. I didn't expect it. How much time do we have?
You have 20 minutes?
Perfect. Okay. So I wanted to talk about continual learning. And it's in a context that I think it's mostly in the reinforcement learning context, but our desire is to push this in terms of lifelong exploration. And you're going to see that many of the issues are similar in these two domains. So the problem setting is the following. we want to have, we want to be able to adapt to continually changing dynamics. And the control theory literature offers many solutions in terms of adaptive control for this case. But it's notoriously difficult to do this with neural networks that adapt online because of the issue of catastrophic forgetting. So the setting is the following. You want to have, you're given tasks over time. Let's suppose for the moment that the boundaries of these tasks are known, and you're not allowed to revisit a task. So every once in a while, someone tells you that you're given a new data set that corresponds to this task, but you're not allowed to look at older data. So you want to train your neural network for task I without retraining on data from the previous tasks. So you want to only spend, you are only allowed to look at each task-specific data set once. Once in the sense that you can iterate over it, but once you finish training on that data set, you're not allowed to retrain on it. So we take a bit more loose approach than online learning, in which case you're actually only allowed to look at each piece of data once. So we spent quite a bit of time trying to categorize and trying to organize the main ideas behind continual learning with neural networks. And I think the main ideas are four. The first one is about increasing network capacity. So the idea is as you get more data, as you get more tasks, you add capacity to your networks, you add weights, and you want to essentially make the new weights focus more on the new tasks and sort of freeze the old weights. And this is the approach followed by progressive networks. The second approach is about essentially trying to move the parameters in a direction that's going to be good both for the old task and for the new task. So in this particular example, the ellipses show, the first ellipse shows a general area where it would be good for task A. And the second ellipse shows a set of parameters that's going to be good for task B. If you directly optimize on for task B, you're going to go directly to the center of this ellipse. But if you optimize while taking A into account, you're going to go more where the red direction is going. So these set of techniques fall under regularization. So you're trying to regularize, you're trying to optimize two things. You're trying to optimize the loss at the current task while making sure that the parameters do not change for the old task. And there are elastic weight consolidation, or EWC, is one of the methods here. There is another method, a very nice method called synaptic intelligence, which has a similar approach, and it tries to figure out, it tries to weigh the changing parameters by saying which parameter corresponds most to a reduction in loss. I'm not going to change those parameters. But if there is a parameter that essentially doesn't contribute much to the loss reduction, that parameter is allowed to change for the new task B. And you keep on doing this over time, where you optimize for the current loss on the current data set while making sure that you're not deviating too much from a previous weights. Then you can do continual learning using repeated applications of Bayes rule. And this is very nice because it just means that you have to essentially apply Bayes rule as faithfully as you can. But remember that theta here are weights over neural network. So you're essentially you're trying to apply Bayes rule on Bayesian neural networks and trying to find the closest, through variational inference, you're trying to find the closest distribution over weights that is going to act as faithfully as a posterior as possible. So the problem here is that every time you try to apply this approximation to Bayes' rule, you're losing something. So you can only do continual learning for a few steps. This particular technique, which is called variational continual learning, and all the flurry of work that has tried to to rely on it, also makes use of adding some capacity to the network, in the sense that for every new task, it's adding a new head theta h to the network. So this is mixing a couple of ideas. In fact, it's missing another idea, which is based on the next component, which is about data replay and core sets. So the idea here is that, okay, you're going to do continual learning, but I'm going to try to, instead of assuming that I should not keep any data from previous data sets, I'm going to try to keep just a few carefully selected data points. And I'm going to include those in the optimization so that I don't forget data from old tasks. And I thought, I mean, we can talk about at length about whether this is cheating or not, according to the definition that we had. But it's undeniable that this actually gives you a lot of bang for the buck, and it improves the results considerably. And there was a recent paper on Archive that showed that an optimal continual learning algorithm, in fact, requires perfect memory in order to be optimal. So maybe there's not a way around keeping core sets. But in any case, we're going to stick with the original definition for the moment, and we're going to talk about regularization type of approaches where you do not keep any previous data around. And the method that we propose here is based on a recent paper from iClear, which talked about continual learning with hypernetworks. And the main idea is the following. You can see it here being applied to the RL domain. But the idea is the following. You have a network, which is this dynamics model, f of theta. We assume at the moment that it's a deterministic dynamics model. And you have another network called the hypernetwork, which takes as input the task definition, the task embedding, and it outputs the weights of the target network. So you have a network determining the weights of another network. So why would you do this? So the main idea is that a hypernetwork can sort of help change the weights of a target network faster than just doing small gradient-based iterations. So it can actually quickly modify the behavior of a target network. So what we do here is, in order to apply this to the RL domain, we interact with the environment using the cross-entropy method. So we plan in the environment for a particular task, we collect some data, we collect the data set for the new task, and then we optimize both the embeddings and the weights of the hypernetwork, such that when the hypernetwork is evaluated on that task and on those weights, it generates a dynamics model that is useful for planning and accurate for planning. So the actual loss function that we have here is essentially improving the parameters and the embedding definition for the current embedding and for the current task, while also not forgetting making sure that the hypernetwork does not change in terms of the weights of the hypernetwork. The weights that the hypernetwork proposes for the dynamics model do not change for previous tasks. So here, the advantage here is that we do not need to keep any data points from the past, but in terms of regularization, we can just say that the hypernetwork should not forget how it generated dynamics in the past. And we can do this without keeping any additional data points. In order to evaluate this, we evaluated on a few robotics benchmarks. So here is a pushing environment for an object that has that is composed of two pieces of different masses, and the different tasks are different have different tasks, different mass distributions for this object. So the same pushing strategy is not going to work when the mass distribution and the moments of inertia change for this particular object. And when you run the model-based reinforcement learning on different tasks like this, you can see that HyperCRL, which is the method we propose, the one in blue, is very competitive with the multitask learning, which has access to all the data from all the tasks. So multitask is the oracle, HyperCRL is our method, and you can see that there's no drop in performance as new tasks are coming into play. So what we show here actually for every row which represents a task, there are dotted dashed lines, vertical lines that delineate the tasks which have been trained. So for row I and column J, it means that it's being tested on task I, and it's being trained on the data from column J while being regularized on the data from the columns up to J. So essentially, being able to maintain your performance while new tasks are being introduced shows, good performance in terms of continual learning, in terms of not forgetting, and in terms of we also quantify forward transfer and backwards transfer in the paper, but I'm not going to show it here. But essentially, this method performs better than synaptic intelligence, than EWC, even better than corsets, which was surprising. So we also evaluated on a few environments that have to do with door opening. So we want to open a door that has different handles, and we want the policy to be able to learn, to not forget what happened from one task to the other, but also transfer information from how to open one door to the other. And here as well, you can see that HyperCRL is competitive with multitask, and all the other methods do not seem to work very well. And notice that I'm plotting a reward here, so accumulated reward. So this is essentially this is not the prediction accuracy of the dynamics. This is how the dynamics was actually used in the problem during planning.
Florian, there was a couple of questions about that work.
Yeah.
Monica, do you want to go ahead?
Yes. Can you tell me? Can you tell us what do you mean by task embeddings?
Oh, right. So every task has to have a vector that represents it.
Sorry, I don't understand.
Right. So you can represent each task as a one-hot encoding. So a vector that says, so we need some way to identify which task we're in. So one way is to say we're, just to give it a number, 1 to 5, for example, in this case. Or we can have a vector that says, I'm at, which activates a vector of 5 elements, which activates the first element if it's task 1, the second element if it's task 2, etc. Or we might want to have a vector of 5 elements, which we optimize so that it's better for the representation, which is what we do. So it's essentially a vector representation of the task.
So it's like representing which task we are doing and not what the task is, right?
Yes, yes, yes.
Okay.
It's just an identifier for the task, a way to, a continuous identifier for the task. It's not a description of the reward function per se. No.
Okay. Okay. Thank you.
Yeah.
So I think that leads into Krishna's question. Do you want to ask your question, Krishna?
Sure, yeah. Like, I was just meaning to ask about how tasks are specified to use, something like task to vec, or do you just design something customized for your setup?
Yeah, I
And
think
what,
we designed in terms of, you mean in terms of the reward function definitions?
yeah, like
Is that
how,
what specifies a task? Is the reward function?
Yeah, pretty much.
okay.
So yeah, let me go back, for example, just to, so here, the task definition for opening the door is you get access to the full state of the door. So you want to make sure that the angle of the door with the current flat configuration is you open the door by 30 degrees or 40 degrees, for example. There are other components to the reward function, which is the gripper close to the door handle? For the circular, or actually for the third handle, is the angle of the handle again at 30 degrees? So you can give extra hints to the reward function for where you want the gripper to be and where you want the handle to be. So these different tasks have different cost functions, which is why when we're plotting them here, we're plotting them in terms of normalized reward in order to be able to compare them. Normalized reward meaning how do they compare to the best performance of an algorithm for that task.
So it seems like it's possible for two different tasks, they could have two different reward functions, but also two different environment setups, right?
What do you mean by environment setup?
Well, here, like the knob changing, I would consider it as like a change in the environment more so than a change in something like a reward function, right?
Yeah. But I think again, since we used a relatively weak model-based RL method, so the cross entropy method, we needed to provide extra hints for the cost function in order to get this to work. So our focus wasn't as much the RL part. It was more how does the performance of the dynamics prediction. Essentially, our question was, do hypernetworks give useful dynamics models over time for a model-based RL method? That was the main question that we wanted to answer.
So yeah, a bit more general question that comes to mind, this problem setup that you're describing with continual learning, that seems like it's most applicable in an RL setting where you wouldn't necessarily like be able to store the data and use it later. Is that how you see it?
I see it in a couple of ways. So notice that the drawbacks of this setting are that first we assume that the task boundaries are defined, which is a huge assumption. And we also assume that we cannot go back to the same task, which is also a very limiting assumption. So what we're working on now is essentially trying to automatically detect task boundaries and task IDs so that we can go back and revisit a task. And that's going to make it a bit more useful in general. I think at the moment this is most useful for RL. My direction is that I'd like to see ways to use this. I'd like to see ways to connect this with some of the contrastive learning approaches that I mentioned earlier. So how do you make sure that these contrastive learning representations can evolve over time without me having to revisit all the data sets that I used to train them? So I think that's possible with these hypernetworks, but we have a ton of work to do in the sense that the hypernetwork has to output all the weights of the network. So if you're using ResNet 18 or anything large and complicated like that, we really need to rethink how we're generating the weights and which weights we're generating from the target network in order to make this happen. So we're definitely not there yet. This is going to take quite a bit of time, but it's where we're going.
Cool, thanks.
Yep.
I have one more question.
Yeah.
So does this put any restriction on state representation across the tasks in reinforcement learning setting? Like these particular state representation can be learned through continual learning and these cannot.
Yeah, good question. So I think the focus here wasn't as much on state representation for this particular iteration of the work. It was more about continual learning of the weights of the dynamics. If we wanted to talk about state representation, it's more related to some of the contrastive learning ideas that I mentioned previously. And especially if those can be used for RL, which is a completely different direction. But I think we haven't, in this work, we haven't done anything that continually learns the state representation. But it's a very interesting avenue, I believe.
Thank you.
Okay. So in terms of future work, in terms of continual learning, I think I already mentioned some of the directions, but I think in terms of environmental monitoring, where we are and where we need to go, I think there's definitely room for multi-step, non-myopic active sensing approaches. I think at the moment, most of us are doing next best view type of estimation for a single step, and I'd like us to explore more multi-step type of approaches. Again, these incremental online updates of human specifications through continual learning, I think that's very useful, very necessary. And we're also working on visual similarity search over spatio-temporal events. So instead of saying record try to find footage like this in a static world, the idea is, here is a video of some useful event. Try to record events that are similar to this. And that's an even more difficult problem, I think, in terms of representations. And the initial results that we have in this scenario are showing that, at least for activity recognition data sets, these representations get more interested in the background of the video than in the actual action that is happening, happening in the video. So there is still a lot of work to do here as well. And of course, larger scale deployments through collaborations with geographers and biologists. I think those are severely missing. Those folks are trying to do deployments without what I would consider the involved and interesting parts of the robotics community, and I think that needs to change. So those are my thoughts at the moment about these lines of work. Happy to accept any questions, and I wanted to say a huge thanks to my former collaborators at McGill for enabling all this work, essentially. So thanks very much.
I mean, I assume they're still your collaborators, right?
Oh, yeah. Sorry. Misspoke.
Okay, I'm gonna end the YouTube stream. Are there any other questions from the